Hey guys, it's Ted, and today we're going to talk about Taylor series. Taylor series are a really important concept in calculus, but in order to understand them, first we have to get under another couple of concepts out of the way. First one is a power series. And a power series is just like any other series that's a sum of is an infinite sum of terms, except it's going to look something like this, where sum from n to infinity of, say, x sub n, where these are all in terms of x. So instead of being just a series of numbers, it's going to be a series of variables. For example, sigma n equals 1 to infinity of x to the n. That's equal to x plus x squared plus x cubed plus dot dot dot. And while normally a series, in order to find if it converges or diverges, you'd have to use some various tests. This, since it's in terms of a different variable than this one right here, this is the indexing variable, it's in terms of a different variable, namely x. We're going to try to find for what x's does this series converge. And a useful test for finding convergence here is the ratio test. The ratio test says if the limit as n approaches infinity of any term over the previous term, the absolute value of that, if that's less than 1, then the series converges. So what this means is, as the terms get out to infinity, we have to have a way to define them in terms of x. And like here, our way to define them is x to the n. So if we were to do a ratio test for this, we do the limit as n approaches infinity of the absolute value of x to the n plus 1. That's the n plus 1th term of the series. And we divide this by x to the n. And this has to be less than 1. So if we simplify this, we get limit as n approaches infinity of, well, this is just x times x to the n. So we can cancel out x to the n, we just get x. And obviously the limit as n approaches infinity of x is just x. Oh, there's still an absolute value here, sorry. So that means the absolute value of x has to be less than 1, because as n approaches infinity, x will not change. So if x is, say, 3, then the series will go off to infinity. That's easy to see, because if we have something that's greater than 1 here, all the powers will get bigger and bigger and bigger, and so it'll easily diverge. But if it's less than 1, then multiplying something that's less than 1 by itself will just make it smaller. So that makes sense. Now, one thing that's important to note is if the ratio test gives you the limit is equal to 1, then it's going to be inconclusive, and you have to figure it out some other way. All right, now we have that out of the way. This is called the interval of convergence. This is just, x is going to be between -1 and 1. This is the interval on which it converges. So that is an important thing to remember, because we're going to actually use that in Taylor series later. So again, let's go over this. So a power series is just a series of functions that are in terms of x. And to determine if a power series converges, you have to find for what x's it converges. Then you do this ratio test, and if you find that this limit is greater than 1, the series diverges. If it's less than 1, the series will converge, and if it's equal to 1, it's inconclusive. So once you do this ratio test, you can find for what x's the series converges, and you get this interval of convergence. So now we can actually start to talk about the Taylor series. And what a Taylor series is going to be an approximation of some function f of x. Let's say f of x looks like this. We're going to approximate it with a power series. It's going to be an infinite polynomial, because that's technically what a power series is if you think about it. It's an infinite polynomial. So in order to approximate this function, we have to center it around something, some point. So let's center it around 0. This is the point 0, f of 0. Now, the way we're going to approximate it is we're going to approximate it as a polynomial, p of x, infinite polynomial. So let's see what it should be. And we have to have various conditions so that it's various conditions so we can get the best possible approximation. First thing we want to do is have P of 0 be equal to F of 0. This will guarantee at least that it's accurate at this point. If we left it at this, if we said, oh, all right, this is our approximation. This is just a line because F of 0 is a constant. This would be our approximation. That's a pretty terrible approximation. It only is exactly equal for a couple points, and that's not guaranteed. Everything else is going to be awful. So now, let's try to refine our approximation. Let's let the derivative of P at 0, we want that to be equal to the derivative of F at 0. That'll at least, we'll have the same slope at 0, so maybe things will be a little bit better. So, the way we're going to do that is, right now, the derivative of P of x is just equal to 0. And that's not what we want. We don't want it to be equal to 0. We want it to be equal to f prime of 0. But notice, since the derivative of 0, that means this term is just a constant. So anything else we add, everything else we add will only be carried down to the derivative. The f of 0 will not be carried down to the derivative because it's just a constant. So if we add f prime of 0 here, watch what happens. Taking the derivative now, we get, this is a constant, we're at 0. Now the derivative is equal to 0 plus 0, which is not what we wanted. So here's what we're going to do. We write an x here. Now, if you notice, taking the derivative of some constant times x is just equal to that constant. So look, we've succeeded. P prime of x equals f prime of 0, and therefore it follows that, P prime of 0 is also equal to f prime of 0. But also notice, if we plug in, if we still want this condition to be true, we still want P of 0 to be equal to f of 0. If we plug in 0 for this, we get f of 0 plus f prime of 0 times 0. So this term will just go to 0. Now that's important here. If you plug in 0, every term after the one we want will go away. If we take the derivative, every term before the one we want will go away. So now, let's try to make our approximation, because right now our approximation is just this line here. Not a very good approximation still, but it's a little bit better. Let's try to make it so P double prime of 0 equals F double prime of 0. The second derivative, if we have the right concavity, who knows, I make it a little better, maybe like that. That already looks better. So, the way we can do that is we can add F double prime of 0 times x squared over 2. And I'll explain why. But first, I again want you to notice that if we plug in 0, both of these terms will go to 0 because we have a factor of x. So this condition is still satisfied. If we take the first derivative now, we get 0 plus f prime of 0 plus, now notice, we have to use the power rule here. We bring a 2 out, and we have 2 divided by 2 times f double prime of 0 times x. And these 2's cancel, and that's why we did this right here. Why we divide by 2, because if we didn't, we'd have a factor of 2 at the end, which we don't want. So now we have this derivative, p prime of x is equal to f prime of 0 plus f double prime of 0 times x. Now, does this look familiar? It should, because this is in the very same form as our last attempt, where we had a constant plus some constant times x. And again, that means if we take the derivative again, this constant will be 0, and this is a constant times x, so it'll just be f double prime of 0. So again, we've satisfied this condition, p double prime of 0 equals f double prime of 0. So again, if you take the derivative, every term before the one you want goes to 0. For example, if you took the first derivative, this term will go to 0. If you took the second derivative, this term and this term go to 0. So that only leaves the one you want. But if you plug in 0, all the terms after the one you want will go to 0. If you take the derivative, this is a constant, you plug in 0, this one will go away. So this Taylor series that we're doing guarantees that when you take the derivative and plug in the center, you'll only get the term you want. And sure enough, the next term is going to be f triple prime of 0 times x cubed. But now can you guess what we're going to divide by? Well, let's see. If we took the derivative of this a couple times, the first time Take the derivative with respect to x of f triple prime of 0 times x cubed. First time, it would be 3 times f triple prime of 0 times x squared. Then if we did it again, if we took the derivative with respect to x of that, then we have to power rule again, bring this 2 out to the front. We get 6, or 3 times 2. I'm going to write it as 3 times 2. That'll become clear in a moment. 3 times 2 times f triple prime of 0 times x. And then again, if you took the derivative a third time, you just get 3 times 2 times f triple prime of 0. So what we're going to divide by here is 3 times 2. That's because we have to apply the power rule multiple times. The first time we'll bring out a 3, then we'll bring out a 2. And likewise, the next one, the fourth derivative, I can use this notation now, of 0 times x to the fourth. The first time we bring down the power rule, we're going to have to divide by 4. Then next time a 3 is going to come out, so we're going to have to divide by 3. Then a 2 is going to come out, so we're going to have to divide by 2. So it goes on like this forever. So now we have a general formula for this series. P of x is equal to the sum from n equals 0 to infinity of, we're considering this, the 0th derivative of f, is equal to, this sum of the nth derivative of f evaluated at 0 times x to the n over n factorial. For example, if we plugged in 3 to the series, the third term, well, technically the fourth term since we start at 0, but the term n equals 4, let's just say n equals 4. We'll get the fourth derivative of 0, just like this. We'll get times x to the fourth, which is that, over n factorial. And remember, n factorial is defined as n times n minus 1 times n minus 2 times ... times 2 times 1. So this is really 4 factorial. This is 3 factorial. 2 factorial is 2 times 1. And this is really divided by 1, which is 1 factorial. And this is also divided by 1, which is actually 0 factorial. 0 factorial is 1, it's not 0. So this is our formula for a Taylor series. And actually, a Taylor series centered around 0 is called a Maclaurin series. So this is a Maclaurin series. All right, that's a Maclaurin series. And notice, this goes on forever, so we can say f of x is actually equal to this infinite power series, this infinite polynomial. A Taylor series is just a Maclaurin series, except it's centered around something else, something other than 0. Looking at that, we'd have our polynomial would be, if we want to center, say, around 2, if we have our graph like this, something like, we want to center around 2, this point 2 comma f of 2. The only difference, we'd have f of 2 here, plus f prime of 2. And now, we want to make it so when you plug in when we plugged in this 0, this term went to 0. If you plugged in 2 to this, you'd have a 2 here instead of a 0. So this term would not evaluate to 0, ruining the series. So what we're going to do instead is multiply by x minus 2. You can think of that as shifting this Maclaurin series to the right 2, because remember, that's what this minus 2 would do. I'm going to make it a little neater. But also it makes it, if we want to evaluate p of 2, we plug in 2 for this, and we get f of 2 plus f prime of 2 times 0. So this will go to 0, and we have f of 2. Likewise, we're going to add f double prime of 2 times x minus 2. We're going to raise this whole thing to the 2, divide by 2, plus ... And the general formula for a Taylor series, centered around A, we're going to center at some point x equals A. It's going to be this. It can be the sum, say f of x is equal to the sum as from n equals 0 to infinity. It's only going to be slightly different from the Maclaurin series formula. It's going to be the nth derivative of f evaluated at a times x minus a to the n over n factorial. Now let's look at what these really mean, because these are approximations that are going to be exactly equal at the point we wanted. Let's say for the first 10 terms, it might look something like this. A pretty good approximation. But we want to find, as this goes out to infinity, how well can it approximate the rest of the function? And for that, we're going to use something called a radius of convergence. So a Taylor series will approximate a function exactly well at the point that it's centered around. But how far can it approximate the rest of the function? For example, if we have a function, we have a Taylor series, if it goes up to infinity, it might exactly approximate the entire function, or it might approximate it perfectly well here, then go off to infinity there and there. Or it might just approximate it here. So we're going to find out for what values of x this series converges. Sound familiar? That's right, we're going to use an interval of convergence. So let's look at some Taylor series of specific functions and see what their interval of convergence is. First one, let's look at cosine of x. We're going to center it at 0. This actually be a Maclaurin series. So the Maclaurin series for cosine of x is going to be, if you remember the formula, the sum from n equals 0 to infinity of the nth derivative of 0 times x to the n over n factorial. So let's just differentiate cosine of x multiple times, and since it's a cyclic function, we should arrive at the same place again. So the derivative of cosine of x, well, first let's find what cosine of 0 actually is, so we can start writing some coefficients down. Cosine of 0 is equal to 1. So our first, this value is equal to 1 here. So we have 1 times x to the 0 over 0 factorial, which is just 1. Now, let's take the derivative. So derivative of cosine, as I'm sure you're aware, is negative sine. So what's a negative sine of 0? Well, sine of 0 is 0, therefore negative sine of 0 will also be 0. So we get 0. That means our second term, the coefficient, is going to be 0, so we don't have to worry about it. All right, let's take the derivative of this. The second derivative of cosine is equal to the derivative of negative sine, which is equal to negative cosine. Negative cosine of 0 is equal to negative 1, which is negative 1. That means our coefficient here, f to the 2, the second derivative of 0 is equal to negative 1. We have minus 1 times x to the 2 over 2 factorial. So we can just erase that. Now, the derivative of negative cosine is going to be sine. So what's sine of 0? Well, that's equal to 0. So the third term doesn't matter either. And then taking the derivative of sine, we get cosine. And we're right back where we started. So we repeat back up here. This equals 1. So what will happen is this Taylor series will actually be 1 minus x squared over 2 plus x to the 4th over 4 factorial plus minus x to the 6th over 6 factorial plus ... where we're going up every 2 terms, because every term with an odd power of x is actually going to evaluate to 0, just because sine of 0 is 0. So we can write this as an actual series, or as one expression. This is equal to the sum from n equals 0 to infinity of, it's going to be x to the 2n over 2n factorial. Because, see, the 0th term will be x to the 0 over 0 factorial, which is just 1. Oh, important thing I forgot. We have an alternating series here. This is alternating, so we'll have negative 1 to the n, yes. That way we ensure every time we have a different sign on the 1. Then the first term is x to the 0, the second term is x to the 2, the third term is x to the 4, or as we could say, this is the 0th term, it's x to the 0, this is the second term, this is the first term is x to the 2, the second term is x to the 4, the third term is x to the 6th. You'll notice this is the 0th term, first term, second term, third term. All these powers are twice as much as the number of terms, so we can just say x to the 2n. And then we're going to divide it by 2n factorial. That way the 0th term will be 1, the first term will be -1 times x to the 2 over 2, which is this, and then so on and so forth. So we can find for what values of x does this converge. And we're going to use, you guessed it, the ratio test. So remember, the ratio test says if the limit as n approaches infinity of any term over the previous term, the absolute value of that, is less than 1, the series converges. So let's plug that in. So we have the limit, down here, we have the limit as n approaches infinity. Now, let's just plug in n plus 1 for every n in this expression. We get -1 to the n plus 1 times x to the 2 times n plus 1. I don't need that parenthesis. Over 2 times n plus 1 factorial. Now, we're going to divide that by, or instead of dividing by, what we can do is just multiply by the reciprocal. Remember, we're dividing two fractions here, because we'd have to divide this term by that term, but both terms are fractions. All right? So here's what we're going to do. We're going to multiply it by just this, the reciprocal of that. We're going to do 2n factorial over -1 to the n times x to the 2n. Let's evaluate this limit. We can definitely cancel stuff out. First thing we can cancel out is this right here, this -1 to the n plus 1 is equal to -1 to the n times -1. And that'll cancel with that. So we have limit as n approaches infinity of -1 times. Now here we have an x to the 2 times n plus 1, which is x to the 2n plus 2. So this is equal to x to the 2n plus 2, which is just x to the 2n times x squared. This will cancel with that. We times x squared. Now we're going to divide this by 2n. The reason why the ratio test is useful for Taylor series is because we have factorials. And the way factorials work is that n plus 1 factorial is equal to n plus 1 times n factorial. So 2 times n plus 1 factorial is equal to 2n plus 2 factorial, which is equal to, in comparison to this 2n factorial, it's equal to 2n plus 2 times 2n plus 1 times 2n factorial. So if we substitute this whole expression in for this, this right here will cancel with that. So we divide it by 2n plus 2 times 2n plus 1. Great. Now, let's see, when does this converge? Well, right here, as n goes off to infinity, this is a quadratic. So this will, this denominator will get infinitely large. So it would go to 0. No matter how big the x squared is, let's say we pick, say, x equals 1 billion. Because remember, we want to find for what values of x does it converge. No matter how big we make an x, this is 1 billion squared, that's 10 to the 18th. N is going to go on forever, so eventually the denominator is going to get bigger. The denominator is going to get bigger and bigger, and it's going to get so big that this is going to be effectively 0. So no matter what we put in for x, this is going to evaluate to 0. And since it's equal to 0, 0 is less than 1. Therefore, it satisfies the convergence test for all x. So the interval of convergence here is equal to, it's from -infinity to infinity. It's all things. Now, let's talk about the radius of convergence. The radius of convergence is, all you have to do is take the center, and this is centered at 0. This cosine it's centered at 0, this Taylor series. So the radius of convergence is just going to be the distance from the center to the end of the interval. And obviously, the distance from any point to infinity is infinity. So the radius of convergence also equals infinity. Now, if it's something like this example that I drew that I don't actually have a function for, if this is our function, this is f, and this is our Taylor series. This is the Taylor series, let's say. As you can see, it only approximates exactly to these endpoints. So this would be the interval of convergence, and the radius of convergence would be this x distance here. All right, let's look at one more very important Taylor series. That's e to the x. E to the x, the important thing to note here is that all of its derivatives are equal to e to the x. So e to the x, take the derivative of that. If we have f of x equals e to the x, f prime of x equals e to the x, f double prime of x equals e to the x, etc. And also, if you plug in 0 for e to the x, you get 1. That means every single coefficient in this formula is going to be 1. In other words, f of x is equal to the sum from n equals 0 to infinity of, I'll just write it out, the nth derivative of f evaluated at 0 over times x to the n over n factorial. But as we said, any derivative of e to the x is going to be e to the x, and if any derivative of x is equal to e to the x, that means any derivative at 0 will be equal to 1. So all of these coefficients will be 1. So we'll have the sum from n equals 0 to infinity of x to the n over n factorial. This is a very simple, the most simple and the most famous Taylor series. This is equal to just 1 plus x squared over 2 plus x cubed over 3 factorial, etc. That's equal to e to the x. That's Taylor series. And let's see what the radius of convergence is for this. If we just take the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n, where these are terms of the sequence rather, this is equal to, this limit is equal to, as n approaches infinity, of x to the n plus 1 over n plus 1 factorial times n factorial over x to the n. And again, this a sub n plus 1 is equal to this term. If you plug in n plus 1 into this equation, this expression for the any term of the series. And the nth term, this should be an n, the nth term is equal to this. And so instead of dividing by this fraction, I multiply by the reciprocal. Let's evaluate this limit. We get is, again, this x to the n plus 1 is equal to x to the n times x. So that'll cancel with this. And this is equal to n plus 1 times n factorial, which will cancel with that. So all we get is the limit as n approaches infinity of the absolute value of x over n plus 1. And just like with the cosine, no matter how big of an x you choose, n will eventually get big enough to make it minuscule. So this is always going to be equal to 0, which is again less than 1. So again, we have the radius of convergence equals infinity, right? Now that's not always going to be the case, obviously. There are going to be functions that can only be partly approximated. But what's important is knowing these formula for Taylor and Maclaurin series. This is the formula for Maclaurin series, and the Taylor series formula is just centered around some constant a. So that was a basic introduction to Taylor and Maclaurin series, how you find them, and how do you find the interval and radius of convergence. I hope you learned something from this video, and if you found this video, you probably know me personally, and I know that AP exams are coming up, so you can either personally ask me what you want to see, because I'm going to be doing some review videos for the AP exam, or even if you want, you can comment what kind of things you want me to go over before the AP exam in a couple weeks. So thank you for watching, and see you next time.